Last class we saw the Chomsky-Schwarzenberger theorem, which claims that push-down automata and context-free grammars are equivalent in power. We also have completed one side of the proof of this theorem, where we discussed about a construction to obtain a single state push down automata from a context free grammar. And in this lecture, we will be discussing about a part of the remaining proof, where we will discuss an algorithm for converting any PDA into an equivalent PDA with a single state. And in the next lecture, we will see how a single state PDA can be converted into an equivalent context free grammar, which is just the reverse operation of what we did yesterday. So let us move on to the topic for today, which is a single state PDA simulating an arbitrary push down automaton. How can a single state PDA simulate or represent a PDA with multiple states? We can try to understand with an illustrative example. Here a PDA is given with the states P, Q, R and S. So there are 4 states and we want to get an equivalent PDA with a single state. Let us see an initial configuration for this machine. Assume that P is a start state, So you are in the state P, reading small a as the input simple, and bot is on the top of stack. And see that you have a transition for that PA bot, it applies. So what is it saying? Move to the state Q and replace the bot with capital ABC. That is what you do. And read head is positioned to the next simple. And now QBA, there is a transition for that. What does it say? QBA, it says pop out capital A and don't push in anything and change your state to R. That is what you are doing here. And now you have the configuration where RCB is a transition that you need, and you have it here. What is it saying? Move to the state S and don't push anything, just take out B, and that's it. So you are getting into a configuration where you need a transition for S, D, capital C, and you have it here. And what is it saying? It's saying you change your state into T and take out capital C, and you can see that the input ABCD is accepted by the automaton by emptying its stack, and if T is final, by both the acceptance criteria. Now question is, how to manage this computation with a single state PDA? Now you have P, Q, R and S, 4 states. How can you manage this with a single state? The only tool that you have is a stack. So what you do is, you try to remember all the other states and these transitions in the stack of the required PDA with a single state. And I am going to tell you the technique that they introduced in part of their proof, and just look at it. What you want to do is, you want to simulate a multi-state PDA with a single state, and what you can do is, you can store simples like this on the stack. So what is this simple? It is a triple, where the first and last elements are states and the middle one is a stack symbol. So in the original stack only the middle symbol is there. Now you are going to store triples where the middle is the original stack symbol and the left and right are states where you can remember what the other states are doing in the original machine. And what is this triple telling is, if the given machine starts processing from the state P, suppose it starts processing from the state P with A as the top of stack, maybe A as the top of stack, then it will pop that A is on the top, it will pop that A and all other symbols that you are pushing to the stack after A, above A. So when you when you have capital I on the top of stack, it is looking at when the machine is going to pop out A and the symbols which are getting pushed on to the stack after A. Example will make it clear. Here, if you look at this transition, where are you starting? You are starting at P with both as the top of stack symbol, and then you can have this kind of a transition. And in the resulting PDA, recall that you need a single state. You call it as dollar. It doesn't matter what the name is. I am calling it as dollar. Dollar is the only state in your PDA. It doesn't matter what the name is. Okay, and it needs to process the same input symbol. And now you are starting at the state P with bot as the top of stack symbol. Then this state must represent the state in which you will pop out all the symbols which are pushed onto the stack after bot. After bot you are pushing ABC. Here you are taking out A. Here B is also taken out, and in this case C is also taken out here. So this is that state T, and I hope you are now getting it. And what is the third component is the state to which you reach after you pop out this symbol and all the symbols pushed onto the stack after bot. So bot needs to be taken out, and all the symbols that you are pushing after bot, this is ABC, and all those needs to be taken out. And which is the state in which you are doing it? It is the state T in which you are taking all the symbols ABC and bot. Okay, I hope you are getting it. And you can define this transition as in the RHS, this is the only state. Now you have to see, you are starting at Q over here, A as the top of stack symbol. Then the question is, in which state you will take out A and all the symbols that you are pushing in after A. In this particular example, after A you are not pushing in anything. So you have to see when you will take out A. You are taking out A in the state R. That is what you are getting it. That is, if you start with Q as the state, A as the top of stack symbol, you are removing A and all other symbols pushed onto the stack later. No such case here. That is in the state R. Now here you are starting in R. The question is, when will you take out B? You are taking out B in S, and that is what you are getting S here. So here you are getting S as the state, C is on the top of stack. The question is, when will you take out C and what state? It is in T you are taking out C. And not that, here actually in the RHS of the production there are three symbols. So you have to say in which state you will take out A, that is this intermediate state R. Then from R in which state you will take out B, which is the intermediate state S. Then from S in which state you will take out capital C, which is T. This can be generalized. And now you look at the next function. Here what you have to define is, from that single state, if you process B as the input and suppose A is on the top of stack, then in which state you will take out A, right? That is in the state R itself. So you can define it as QAR. and the RHS will be what? The number of triples here you need is same as the number of elements in the string in the RHS. Here it is 3 because here in this case it is 3 because you have 3 simples. Here you can note that there are no simple, so in the RHS this will be epsilon. So it follows the definition. That means if you start in a configuration where Q is the state, A is on the top of stack, then you will get in the next step taking A out of the stack and you are landing up in the state R. Okay, so in the new machine you don't have to push any triple, and that's it. And similarly, if you look at this configuration where you are reading small c, you are in R, B is on the top of stack, and you are popping it out in a single step. So in the RHS you don't need anything because here again the RHS is epsilon. Similarly, you will get transition for the last transition in the original machine, and what will be it? This is what you need in the LHS. You are reading D, AC is your state, C is on the top of stack, and because in the RHS epsilon is there, you can pop in the new machine as well. I hope you are getting me. For the interest of time, I have to proceed. If you are not getting, please watch it again. So these are the transitions that you are getting in the new single state machine. And now you see what you do in the new machine. Not that this is the only state and the start state. And this needs to be the bottom of stack simple. That is the original start state of the machine, bottom of stack simple of that machine, and the final state in that machine. Assume that there is a single final state. So that is the bottom of stack simple that you need in the new machine. The original start state, the original final state, and the original bottom of stack simple. That is the triple defining the bottom of stack simple for the constructed single state PDA. And not that now there is a transition that applies $A P bottom T, that is this transition, and if you apply it, what you are saying is remain in dollar, you push in these 3 triplets. That is exactly what you are doing here. Now if you look at this configuration $B QAR, and you have a transition here, just apply it. It says you pop out this. Now if you look at this configuration, it is $C RBS. This is the transition that you can apply, you are taking out. And here it is D SCT is this transition, again asking you to take out, and see that the new single state machine is also accepting the same string because that is accepted by the original machine. So that is an example, and now we can try to formally define how can you define a transition function in the required machine based on a transition function in the new machine. Now in the new machine, this is a transition. The question is, P is defined by this state of the original transition function, A is the same input simple, and what is this bot? This is exactly the bottom of stack simple from the original transition function. And what is not known to us is the states that you need here, here and there, and we are getting in this particular example it is R, S and T. The question is, how will you find it? Actually there is no way, because you not that if you start in this configuration where Q is the state, B is the next input simple, capital A on top of stack, it may happen that eventually after A you are pushing in some more simples, a string is pushed on. Okay, so you don't know actually in which state you will take out A. So the state R can be any state in the given machine. So you have to consider many transitions where this state can be an arbitrary state of the original machine. Similarly, S and T. Okay, so what we are telling is, let the single state PDA non-deterministically guess the state R, S and T. So, you have to add transitions for every possibility of R, S and T. Okay, and for this is what I am telling. Now, look at this configuration, and suppose it happens like this. It means you are taking out that capital A in a single step, and then you can add that transition, and in general this could be a transition in the original machine. And what is it saying? If you are in the state P, you are reading the small c as input and capital A on top of that, then what do? You consume that input, change your state to Q and replace capital A with a string of variables V1, V2, etc. Bk. And if you generalize this, you will get it as in the new machine, dollar is your state, C is the same input simple, P is this state of the original transition, A is this simple, and nothing else is known. And you know that here there are K simples, so K triples are required here. So you, and the first state of this triple is given by the state in the RHS of this transition. So what I am telling is, dollar is the only state, C is this input simple, and P is given by the state in the LHS of the original transition, A is given by the top of stack simple, and now what is QK we don't know, we have to see. In the RHS, dollar is the only state, and the first state in the first triple is defined by the state in the RHS, that is fixed. And you don't know about all these states Q1, Q2, etc., Qk. That you have to non-deterministically guess. So you have to add transition for every possible values of Q1, Q2, etc., Qk. It can be any state. And not that you have this string B1, B2, etc. Bk. So you have to see after B1 which will be the state in which you will end up, similarly for all other simples. And so you need K states, and each one can be any state in the state set of the original machine. And not that the last state here where you land up after taking all these strings, all the simples in the string, and the same state is coming here as well. I hope you are getting it. Otherwise, please watch it again and you can see what exactly they are trying to do. And when this simple is empty, you know that in the RHS also nothing is required, you can pop out. So you can add this transition in the required machine, because in the RHS not triple is required because no simple is there in the RHS. So now we can try to apply that construction on an example PDA. Here is a PDA with two states P and Q, and the PDA is for accepting this language, and we will apply that construction to obtain a single state PDA. The state is going to be dollar, and we can see how it works. These are the rules that we obtained in the previous slide. I just copied it. Now see how you will get a transition corresponding to this transition in the original machine. This is what you can add, where the input simple is same as the input simple of the original transition, and the first state in the first triple, in this LHS triple, is the state of the LHS in the original transition, and the second or the middle simple in the LHS triple is the bottom of stack simple in the original transition, and that is what we already know. And also we know that in the RHS, the first component or the state in the first triple is the only state in the RHS. Whatever be the state in the RHS, that is going to be the first element or the first state in the first triple of the RHS. And we know one more thing, which is that whatever be this intermediate state, that can be any possible state. So, you have to try all possibilities of P and Q in these positions. So, you have to add all those transitions. So, this intermediate state can be either P or Q, and the last state can be either P or Q. And why you are getting two triples? Because two simples are there in the RHS. And also note that whatever be the last state here, that will be the state that you need here. QK is same as this, is what I am telling. And these are what we know. And now you will get another transition where P is taken as the last state, and you are getting two transition where this state is either P or Q. When you substitute P as this intermediate state, you get this transition. When you substitute it as Q, you will get this transition. Fixing P as the last state. Now, if you substitute Q here, you will get this transition when the middle state is P. So, you will get one more transition when you fix Q as the last state and Q as the intermediate state also. So, these are the four transitions that you will be getting by substituting this intermediate state as P or Q and the last state as P or Q. And everywhere last state is going to be the last component here, you can verify it. Yeah. And now if you move on, for this transition as well, you will get four transitions, you can verify it offline. And if you move on to this, you will get a single transition. You can just take out, this is the rule that you are getting here. Similarly, for this you will get one transition, and for the last transition as well. For the interest of time, I am progressing from here. These are the set of transitions that you obtain, and now we can try to apply this on an input string A square B square. Not that this is the initial configuration where the only state, read head to the first symbol of the input, and the bottom of stack symbol is the start state of the original machine, the end state or the final state of the original machine, and the bottom of stack symbol of the original machine. And now note that this is the transition which applies $A P bottom Q. And what does it say? It says push in these two triples, and that is what you are doing. Now if you look at this configuration, you can apply this transition. There are many. Suppose you are applying this non-deterministically selecting. $A PAQ is what you have, and what does it say? Push in two more triples, and this is what it says. And if you look at this configuration, you can see that this is the transition that you can apply, or this is a transition that you can apply, that is $B PAQ. And what does it say? Just pop out. And now you have $B QAQ, and now you apply this transition. If there are many, you can non-deterministically select one. What does it say? Just take out. So this is what you are getting. And what is the configuration? Nothing is there, QTQ, and here is a transition for that. Without processing an input symbol, QTQ, sorry, Q bot Q. What does it say? Take out. And note that the input A square B square is in the language, and the unique state PDA is accepting it. And you can simulate it for any input in the language or not in the language and see how it works. And with this, we are coming to a slide where I am formally defining the machine. Idea is to remember the state in the stack, and the states in the the simples in the stack is going to be triples, the first and last of states, and the middle one is an original stack symbol. And suppose the newly constructed machine accepts W from the initial configuration, then we can prove that the original machine also accepts that string. Okay, this is the transition rule. There are two rules: when there are simples in the RHS or when there are no simples in the RHS. I am just copying it. Now we can formally define it. Given a multiple state PDA, you can construct a single state PDA without loss of generality. Assume that there exists a single start state and a single final state, otherwise you can make it satisfy this. And the new machine is going to be this. What is it? This is the only state, and alphabet set is same. The only change is here the stack alphabet is going to be triplets, that you know, and this is the only state becoming the start state. Transition functions that we defined, we can recollect it later. This is the bottom of stack symbol, the start state of the original machine, the bottom of stack symbol of the original machine, and the single final state in the original machine. And we are going to accept by empty stack, so you don't want to get any final state. And transition, there are two rules. This is the first rule that we found, and this is the second rule, and that is how you can define a single state PDA from an arbitrary PDA. And with this, we are coming to the last slide, where I am giving you an exercise problem for you to practice and understand how can you convert a multi-state PDA into an equivalent single state PDA. Here the PDA is given for this language. So what you do, you apply that construction, obtain a single state PDA, and you simulate your single state PDA on these three inputs. There are strings in the language and not in the language. You see how it's going to work. Today we looked at a procedure for obtaining a single state PDA equivalent to a multi-state PDA. Thank you.